Generally, for any process, we can have initial state and final state. And when we want to calculate the enthalpy change of this process, then we just take the enthalpy of the final, enthalpy of the initial state, and we calculate the change of the enthalpy as a difference between these two things. And you probably remember sublimation is change from solid into gas. That would be exactly equal as the enthalpy of fusion, so change from solid to liquid, plus the enthalpy of the vaporization. Why? It's very simple to see. This one is the enthalpy of fusion, so liquid minus the enthalpy of solid, plus this one is the enthalpy of gas minus the enthalpy of liquid. Now you see that liquid enthalpies just simplify, and you get that this is Hg minus Hs, which is of course the definition of that one. So what is important is that there may be some intermediate state and the reaction or the process can go directly from here to here, or maybe the process go first here and then here. We don't see it in the final results. The final results doesn't depend on the path. So, important thing is that when you have the change of enthalpy in a reaction, this is equal to all possible enthalpies of products minus all possible enthalpies of reactants. So as you see, this is very, very simple. Now, the reaction can have 1 step, 2 steps, 3 steps. You don't care, because you don't care for any intermediate. You are only interested in the initial states, so reactants, and the final states, so products. Good. Now, this is very important because it gives us an opportunity to define something what we called formation enthalpy. Which is written in the usual way like that. We have formation of AB. We have one element and another element, and these two elements make a molecule. But on the last class we said that by definition enthalpy of A is 0. And we also said that enthalpy of B is 0. Because enthalpy of an element in its standard state, it's always 0 by definition. So we have very nice, because the enthalpy of formation of AB is just equal to the enthalpy of AB minus the enthalpy of A minus the enthalpy of B. But we just said that these two are 0. So finally you get that this is A enthalpy of AB. Good, so it's kind of solved the problem. What does it mean, enthalpy of the reactant? You see that the enthalpy of AB is just equal to the enthalpy of formation of this AB. So how to measure this thing? Well, for example, you mix element A, element B together, and you just make the reaction and check how much heat was released. And this in experiment gives you the enthalpy of formation of AB, and by this equation it's exactly equal to enthalpy of HB. AB. Good. This gives us an opportunity of going to the next step, and namely we do the next step like that. When we want to calculate the enthalpy of the reaction, we have, for example, AB reacting with CD, giving us AD plus BC. And we want to calculate this enthalpy reaction. How to do this? Very simple. First thing, you just do one additional step. In this one additional step, you just get H plus B plus C plus D. And in the second step, you just make this. You clearly see that coming from here to here, I'm just creating AD. So this one would be enthalpy of formation of AD. And I'm also making BC, so plus enthalpy of formation of BC. Now here, if I'm coming this direction, then that would be enthalpy of formation of AB plus enthalpy of formation of CD. But I'm going the opposite direction, so it would be just the minus enthalpy of formation of AB minus enthalpy of formation of CD. Which gives me finally my equation saying that path from here to here must give me exactly the same result like the path from here to here. And this path is minus enthalpy of formation of AB minus enthalpy of formation of CD plus enthalpy of formation of AD plus enthalpy of formation of BC. And you probably can notice immediately that this is nothing else like what we said a moment ago. Summation of enthalpy of products minus the summation of enthalpy of reactants. Good. Let's use this for some example. Before we use it, just one more important thing. Very often, instead of writing this and instead of writing this, people are writing the following notation. Now, what is this small circle? This small circle denotes standard conditions. So saying in other words, it means that the pressure is equal to 1 atmosphere. Good, let's do example. Find enthalpy of combustion and combustion is an important word. Combustion means that you have a reaction with oxygen. And now of 100 gram of C3H8. That's the problem to solve. What you have to do is C3H8 plus oxygen going to CO2 plus H2O. Now, 3 carbons for waters, 3, 2, 5. 1, 2, 3, 6, 10, yeah. Good. That would be the enthalpy of combustion, very often written with a small c here. We have to find this thing. How to find this? Well, like always, first we decompose this one into carbon, and you know that we need the carbon in this original state, and that would be graphite. And you see that there are 3 of them. Then there would be 4 hydrogens in the standard state, which is a gas, and plus 5 oxygens in the standard state, that is gas. Well, we should also write what are these things. This is gas, of course. This is gas. This one can be either liquid or gas, so we just keep it like that. Gas. Now, if there is liquid or this is gas, the result would be different, because to come to gas or come to liquid, they differ by the vaporization enthalpy. So we have to assume one of them. We can assume, for example, gas, but we can calculate the same later for the liquid. We just get different number. Okay, what is the enthalpy of this reaction? This is clearly the minus enthalpy of formation of C3 of a propane. check the oxygen didn't change. We have just a opposite formation of the propane. What about this direction? This is 3 times the enthalpy of formation, of course in the standard conditions, but because that's what we want, of CO2, plus 4 times the standard enthalpy of formation of H2O. So finally we are getting here that combustion enthalpy of this reaction would be equal to 3 times and after putting the data, this, and this inside, you have the solution. How to get this data? Well, they are at the end of your book, in the appendix number 1. Formation enthalpies for many chemicals are listed there. And usually to solve problems, you need this data. We are just skipping this part. You just don't calculate the final value. Good, let's go further. There is the following question. Enthalpy of formation is larger than 0 or smaller than 0 for stable molecules. Good. I give you an example of formation enthalpy of 2 things. One is the formation enthalpy of CH4, methane. And another one is the formation enthalpy of C6H6. This one is minus 70, minus 74.8 kilojoule per mole. This one is plus 49 kilojoule per mole. Turns out that I don't say random, but can be both. Usually for big molecules it's positive. So making a big molecule requires energy, in fact. But making small molecules usually gives you energy. Good. So you see that stable molecule doesn't really depend on the enthalpy of formation. So this is not a good way of judging if something is stable or not, only looking at this number. And we will learn next class what is the number to find if something is stable or not stable. You see that both of them, both methane and benzene, they are both very stable molecules. Okay, let's go further. Well, the thermodynamics is very often a science of just solving problems, so we should know how to solve problems. One of them is how much energy is needed to heat 100 grams of water from 80 degrees Celsius to 110 degrees Celsius. Question is very simple, but we should consider what's happening in this process. So first, you have 3 stages. Stage number 1 is heating liquid from 80 degrees to 100 degrees. Stage number 2 is vaporization. And stage number 3 is heating gas water from 100 degrees Celsius to 110 degrees Celsius. Good. So, how much energy? We had heat 1, heat 2, and heat 3. And finally, we calculate the total energy needed for this just by adding these 3 numbers. Now, the exercise doesn't tell us if this is a constant pressure or constant volume. Well, we can assume something. So we assume constant pressure. If this is constant pressure, then we know that heat is just equal to the change of enthalpy for every process. If we assume constant volume, then we have to use internal energy here. But let's use this. Good, let's calculate the first one. Heating liquid from 80 to 100. This is a physical process, and you know that the heat capacity at constant pressure was defined as Q over delta T was defined as delta H over delta T. From this one we are getting the change of enthalpy is the heat multiplied by change of temperature. Very nice. We know that Q1 is equal to heat capacity of water in the liquid phase times the difference in temperature. Now we go to the table and we find this heat capacity. Turns out that heat capacity for water, for liquid water, is 75.29 joule per Kelvin per mole. And now change of the temperature is 20 degrees. But there is one problem. Here we have mole, and here we have 100 grams. Okay, so we have to change the units from grams to moles. So this is enough to multiply this equation here by the mass divided by the molar mass of water. So times mass is 100, molar mass of water is 18. And again, if somebody has calculator, we get a number, whatever the number is. Then Q2. Q2 you calculate in a similar way. It's the heat capacity at constant pressure of the water, but this time not of a liquid water, but of a gas water, times the difference in the temperature times the change of grams to moles. And this is again equal. This one we go for tables and we are checking that this one is equal 33.58 joule per Kelvin per mole times the difference in the third process is from 100 to 110, so the difference is 10. So 110 times 100 by 18. And again equal to some number. This is of course equal Q3. Good, we calculated already two things. By the way, looking at this one, this number has here 75 as a coefficient, and here is 33. Looking like heating liquid water requires much more energy than heating gas water, because you have to break the hydrogen bonds. Here there are no hydrogen bonds anymore. Good. What happens if the Q2, vaporization? That would be easy again. That would be the standard enthalpy of vaporization of water, and this is per 1 mole. So now we have to change it to the grams we have. And again we go to tables, we check what is the standard vaporization of water, and I already multiplied these things in my paper, so I don't know. But totally it's 40.7 kilojoule. Maybe I didn't multiply. No. It's 40.7 kilojoule per mole times 100 divided by 18. But now notice the following thing. Here, joule. Here, joule. Here, kilojoule. This one is 1,000 times larger than these things. So it looks like that the total energy of heating water from 80 to 100 really coming from this energy. This one, if you really don't have time to calculate, you can skip and you get still almost correct answer. There will be very small corrections to this Q2. Q2 is probably 98% of the total answer. Well, maybe even more. 99. Good. So this is one of the examples. This example gives us some idea about the so-called heating curves. And the heating curves showing you the following. Showing you how much heat you give to your system and how much the temperature is changing. So if you have some starting point, let's say here, and you start heating, you are putting the heat inside and the temperature is growing. And then finally, there is a point when you put the heat inside but the temperature is not growing. And then again, you are putting the heat inside and again the temperature starts growing. And again you have flat line. And again you have like that. This is called heating curve. Here you are heating solid. Here you are melting the solid. Here you are heating liquid. Here you are vaporizing. And here you are heating gas. Now the important part is that temperature doesn't change here and here. Second important part is that these curves have different slope. Because generally solid, liquid and gas has different heat capacities. Good. Final examples on this one. That will be practical one. What gives you more energy? One apple or one beer? Let's try to use the data. And let's try to use chemistry to judge what gives you more energy. Okay, of course we have to do many approximations. First, that apple has only sugar. And I'm assuming here that one apple has 15 grams of sugar. So clearly this is not a Taiwanese apple. Taiwanese apples are more sweet. Okay, let's assume that in beer you have approximately 25 grams of vodka, of ethanol. Sorry, once again. 25, 0.4, then 10 grams of pure ethanol. Okay. So I'm just assuming. Of course, everybody knows that beer has also some sweet. It's called malt, and this one has a lot of calories. But I just skip this part. Now, second thing, I'm assuming that if you eat sugar, your body will totally produce the sugar into heat. I'm also assuming that the alcohol is 100% produced into heat, which is not always the case. As you see, many Asians drinking alcohol become very red. So, still, the assumptions. Let's go further. Now, we need the two following things. We have to know how much in moles it is and how much in moles it is. Turns out that the molar mass of sugar is equal to 342 grams per mole. And the molar mass of ethanol is equal to 46 grams per mole. So it turns out, if you divide these two things by each other, you find that this is equal to number of moles of sugar is 0.04386 mole. And the number of moles of ethanol is 0.2174 mole. Good. Now we need to know what is the standard enthalpy of combustion. Because what's happening in our body is sugar and alcohol are connecting with oxygen and produce CO2, H2O. That's just combustion. So what is the combustion of sugar? And what is the combustion enthalpy of ethanol? As you see, I'm writing HOC2H. It doesn't matter how you write it as far as it's clear what it is. Okay. Again, you go for tables to check these two numbers, and turns out that this one is minus 1,368 kilojoule per mole, and this one is minus opposite 1,368 kilojoule per mole, and this one is minus 5,645. Good. So you are able to multiply these two numbers, and you find that one apple gives you around 59 kcal. Well, I mean, you calculate it as 247 kilojoules, but usually the calories are given in these units, so I exchange it so that you can compare directly with Tic Tacs, for example. And one beer gives you more or less the energy of 297 kilojoule, which is equal to 71 kcal. Well, we have the results showing that it's better to drink even cold beer on the cold day than eat an apple to get warmer. But this is, I'm not suggesting anybody to drink alcohol. So. Okay, let's go further. There is something called Born-Haber cycle. And I'm not going to teach you what it is. It is in the books. There is one chapter on this, so you just learn by yourself. It may be on the final exam. Unfortunately, we don't have much time left, and there was no class this Tuesday, so it's supposed to be on Tuesday. Good. So Born-Haber cycle you learn by yourself, and I think by doing this we finished the chapter number 6. And we can shift to chapter number 7 and discuss entropy. What is entropy? I will teach you more on the next class, but today we just do a molecular examples. How much time we have left today? 10 minutes. Yeah. You see the speed of today's class is a bit high. Well, let's try. We start with defining entropy as a measure of disorder. Entropy is very often denoted with the letter S, and entropy is a function of temperature. Is it? Maybe not. And what it is in a thermochemistry, we will study in the next class. But today I wanted to show you what entropy is in the molecular case. So instead of saying it's a measure of disorder, which is a nice sentence but doesn't mean much, I try to give you another definition as a mathematician, which would be K and this is Boltzmann constant. And W is number of possible states of a system. One day later, when you will be learning statistical physics, you learn that this is called partition function. And you will also learn that this is only true for the so-called microcanonical ensemble, but we are skipping all these things. And let's give the example of entropy. We are going to use this definition. We are going to count the number of possible states for some particular systems. Now you have 10 particles. First thing, they are non-interacting. Non-interacting. Very nice, because it means there is no potential energy, there is only kinetic energy. Now, every particle can have energy equal 0, 1, 2, 3, 4, and 5. What does it mean? It means that there are 5 different energy levels, 6 different energy levels. With the energy equal 0, 1, 2, 3, 4, and 5. So now every of these 10 particles can be here, 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 or here, in one of these levels. Good. Now we are going to calculate the following thing. Number of possible states of all particles if, and now I'm writing E if total energy is equal to 0, it means that every particle is at this state. So first particle is here, second particle is here, third particle is here, all possible particles are here. So the number of states is only 1. And this particular state looks like that. This particular state that I'm discussing now looks like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What happens if the total energy is equal 1? That's a difference. Because now we can take any of these 10 particles and we can put it here. We know that 1 can be decomposed into 10 as 1 plus 0 plus 0 plus 0. So the number of possible states, of course, it's 10. Because the first particle can be here. We know that generally it will look like that. But it can be the first particle, it can be the second particle, the third particle, fourth particle, and so on. Good, let's go further. If the total energy is equal to 2, we can have two different situations. The first situation, that 2 is equal to 2 plus 0 plus 0 plus 0. And second situation, that 2 is equal to 1 plus 1 plus 0 plus 0. The first situation corresponds to situation when the first situation when one particle is here at the second level and all others are at the first one. How many possibilities of realizing this? Clearly, number of states would be 10 here. What about this one? Here is a bit more complicated. Here we have two particles shifted here. It can be particle 1 and 2, 1 and 3, 1 and 4. We have to calculate all possibilities of this. And turns out that number of them is equal 10/2, which is 45. So the total number of possible states available if the total energy is 2 is 55. Good. As you see, you can go farther and farther and farther. Now, what is the good part of this? Now we can use and calculate the entropy. If the energy is equal 0, the entropy is Boltzmann constant times the logarithm, and here is the W, the number of possible states. And we just calculated that the number of possible states here is 1. Then you have K multiplied by the natural logarithm of 1, which is 0. And you found that the total entropy in the ground state is 0. Is it the lowest possible? If you look at the definition, yes, because logarithm is positive function, is non-negative. Well, of course, assuming that this is number of possible states, so a natural number. The lowest possible one here is 1, and then the logarithm will be equal to 0. What happens if energy is equal 1? Then you have S, K, logarithm of 10. What is the natural logarithm of 10? It's a bit larger than 2, I guess. So you have like 2.2k. What is the for 2 states? S is equal k times natural logarithm of 55, which is 2.7392781. It's 3.7k. I'm just approximating this, so. So you see that more energy the system has, the entropy is growing of the system, because the disorder is larger and larger. Every particle can be at different levels. Okay, so why I started from here is that this one gives you a way of calculating entropy and gives you a real number for each of them. What I will be showing you in the next class is the thermochemical definition of entropy that doesn't give you that feeling like that, but gives you a tool of calculating real things. And I think it's a good moment to finish this class today. Thank you.